Welcome to physics. We are now on activity 3 of our energy unit, and we're going to be exploring further and introducing a little bit work and kinetic energy. Excuse me. So, to start, work is really how we connect the terminology and the calculations between forces. So if you think back to when we did forces, motion, and momentum, uh, we are now connecting that to energy through work. So work is the product of the net force on an object. And so again, when you think about net force or remember back to net force, that was let's say on an object, let's on box. Okay, there's these forces. Gravity's pulling down, and if someone's pushing the box, there's a force going the direction of the push, and then there's also a force in the opposite direction. And if the box is on the ground, then there's also a a normal force, which is pushing up, right? And so the net force, when we talked about forces, allowed for motion to occur. So if one force was greater than the other in the opposite direction, then it was moving. Okay, and then since we've introduced energy, we've been talking about how energy really is motion. So that they are really kind of one in the same, and they allow us to talk about it two different ways, though. So the product of net force on an object and the distance through the object through which the object is moved. So again, when we talked about net force, we said, okay, how much force does it take to move an object? Well, now we can determine how much work there is, or how much work it would take um, when you apply a net force for a certain amount of distance. Okay, so how much work would it take to move the box, let's say 5 feet, right? Not just move the box, but move it 5 feet. So now it is a slightly different piece of information. And just like we did with energy, it also will be in joules. Okay, so work you'll see as W, the unit is going to be joules, and how you calculate work is going to be the net force times the distance in meters. Then again, kinetic energy, we've talked about this a few times now. It's the energy of motion. If there is motion, then there is kinetic energy. And so now, how do we calculate that? It's going to look like that. So it's going to be half mass times speed squared. And another way of looking at it will be like this. Okay, so really, if you know the mass of the object and you know the velocity in meters per second, then you're going to be able to calculate the kinetic energy. Okay, but now here's another aspect. How are work and kinetic energy related? So we're going to look at this, and so kinetic energy of a moving object is equal to the work required to bring it to its speed from rest, or the work can, or the work an object can do while being brought to rest. Okay, so kind of the opposite. And so one way you can write that is the net force times distance, which should look familiar, equals kinetic energy. And then again, another way of writing that is your net force times distance equals half mass times velocity squared. So, in other words, your kinetic energy is equal to your work. Okay. So now we're going to practice that a little bit. So you're going to want to refer to those up above. And here's scenario 1. Okay. So you have a box with a net force. Okay. This is kind of right, a basic one. I've given you the net force of 300 newtons, and you have pushed it 2 meters. Okay, so calculate the work required to move this box 2 meters. And again, it's in joules. So you're going to want to refer to net force times distance. Okay, Then, again, do we understand how work and kinetic energy are related? So, how much kinetic energy is present in scenario one? Boom. If you moved it 2 meters, 300 newtons, okay, how much kinetic energy is present? Scenario two, we now have a box. Ooh, okay, 500 newtons down, 200 newtons up. Again, that means it's falling. If you have a net force in the downward direction, that means it's falling. And 200 newtons could be something like air resistance, okay, kind of pushing back up on it. But it's important to know that it's not balanced. So you find the net force, and then you can say how much kinetic energy is present if it has fallen 6 meters. Okay, so again, you're actually going to be using this equation for that one to get your kinetic energy. And then how much work is required to bring the box to rest after falling 6 meters? And my hint for that, again, is how are they related? There's a key piece of information in here that talks exactly about what that question is. Scenario three, here we are. So a car with a mass of 2,000 kilograms is traveling at a velocity of 15 meters per second and runs a red light. So how much kinetic energy does the car have while it runs the red light? You're going to want to look up at our kinetic energy calculation with mass and speed. Don't forget to square it, okay? So that'll give us here. If the car ran into another vehicle and the intersection came to a stop, how much total energy would be transferred into the opposing vehicle? This really requires you to think back to our previous activities, assignments on energy transfer. Okay, and my hint to you would be energy within a system. Okay, what does the total energy in a system look like? So think about that as you look to answer this. And then, of course, if you have any questions, I would love for you to attend. And if you're unable to attend class, please email me if you have questions. Okay, this one is the one I expect will take the most time, but I actually tried to set it up for you to practice Desmos a little bit. Okay, we've introduced Desmos in first quarter. We haven't used it for a little bit, but it is still very useful, and so I wanted to do this. But we're going to look at a skydiver with a mass of 70 kilograms jumps out of an airplane and begins to accelerate towards the ground. That's just a broad scenario. Okay, you are going to then fill in the table and demonstrate the relationship between the skydiver's velocity and kinetic energy. So to do that, I have given us a table, okay? But really, I want you to use the Desmos template. So it's something to keep in mind when we're looking at this. I've given you the velocities, okay? You know the mass. So if you know the mass and you know the velocity, then you can solve for the kinetic energy. That being said, oftentimes it's easier if a computer will do it for you. So I'm going to open this template that I've created for you and show you how to use it. So this right here, even though the titles are slightly different, X1 and Y1, this is the same table. So here are your velocities. Okay, you'll see velocity is down here across the bottom. And here is your then kinetic energy that you're going to be solving for. And to help you, I entered the formula, and then you have these sliders. So again, if M is your mass, it is already set to 70 kilograms. So you don't want to change this value. Okay? But now your velocity, okay, you want to fill in the table. So your first calculation is going to be for 0, but you already know 0. It's everything would be 0. So you're going to get the answer to your kinetic energy right here. So the each of these then go by 5. So if I click this, now the velocity is 5 meters per second. And my y value, which is kinetic energy, is 875. So I can fill that in. Okay, then I can click to the next one. Whoops. And it's 10. Okay, so the velocity is now 10 meters per second, still keeping my mass the same, 3,500. So you can go through and fill in this chart. 7875, 7875, and again, those are going to be joules. So 7,875 joules of energy, kinetic energy, with a velocity of 15 meters per second. And then you can see that the data points start to have a trend that should look very familiar from Q1. 20, okay, 1,400, or 14,000, I apologize. Okay, and so again, you're going to see this, and there's going to be a question about the relationship between kinetic energy and velocity. So again, that's how you fill it out, and it's really, you just have to click, wish it stopped jumping up, this slider and record this value as you go down into your data table. So again, I do want this data table to be transferred into here. Okay, and then I want you to insert a picture. So just a reminder, on the picture, there's this little share graph button. You can do, I believe, print, and it's going to give you a little picture preview that you can save in Google Drive. You can save as a PDF, but you can see that's an image. You can export image as well. Okay, you click that. It kind of shows this for us. Okay, and then you can download it, or you can take a selective screenshot of your data table and your whole thing. Then again, in here, here's your little picture button. You can select where you want to get it from and embed that picture. So please let me know if you have any questions about that. But this Desmos will make that job very, hopefully, quick for you instead of having to enter it in your own calculator. And then complete the sentence. As you increase velocity, you blank kinetic energy. Okay, find the word that's going to fill that in for you. So that is our activity. Again, exploring the relationship between work and kinetic energy. Let me know if you have questions, and thank you for all your hard work.